Welcome to The Explainer. Today we're diving into a masterclass on demystifying backend networking. We're going to break down the exact anatomy of HTTP. And, think of it not just as some rigid technical protocol, but as a highly structured conversation. It's a strict set of rules that lets the entire web talk, share, and just function seamlessly.
Okay, let's dive into this. We'll start with the heart of HTTP, move into the anatomy of a message, explore methods and intent, navigate cores, decode status codes, and finally, wrap up by optimizing the flow. So let's start with a really fundamental question. How does your browser actually talk to a server, right? Behind literally every click on a website, there's this strictly governed dialogue happening between a client and a server. Operating at the top application layer, this communication absolutely needs a reliable medium. So it typically relies on a TCP connection. It establishes a super reliable handshake to ensure absolutely zero messages are lost before a single piece of data is even exchanged.
All right, part 1, the heart of HTTP, the rules of engagement.
To really understand where we're at, we got to briefly look at how this protocol evolved to solve some pretty major performance bottlenecks. So, back in HTTP 1.0, every single request opened a brand new connection, which, was incredibly inefficient. To fix that, HTTP 1.1 introduced persistent connections, keeping the line open for multiple requests. Then, HTTP 2.0 brought us multiplexing, allowing multiple requests to fire over a single connection simultaneously. Real game changer. And today, HTTP 3.0 actually shifts away from TCP entirely. It uses UDP over the QUIC protocol to drastically reduce latency and handle packet loss way better.
And this whole evolution brilliantly illustrates the dual nature of HTTP's foundation. On one side, we've got statelessness. Basically, the server has amnesia. It has absolutely zero memory of what you asked it just 5 seconds ago. Every single request must be completely self-contained with all the data needed, like cookies or auth tokens, for that specific interaction. On the other side, we have the client-server model. The client, like your browser, must always be the one to initiate the communication. The server is literally just sitting there, waiting to process and respond.
Moving on to part 2, anatomy of a message. What's actually inside?
Well, at the very core of these messages are headers. Headers are key value pairs that provide vital metadata about the request or the response. They essentially dictate the client's environment, its preferences, security policies, and how the server should ultimately format its response. Things like the user agent to identify the browser or authorization to pass a bearer token, all of that lives right here in the headers.
But, looking at this setup, a pretty logical question pops up. Why do we need a completely separate section for headers? Like, why not just shove all this configuration and metadata right inside the request body itself?
Think about it using a real-world parcel metaphor. When you ship a package, you write the recipient's address and details on the outside of the box. You don't seal the address inside. If you did, every single courier along the way would have to rip the package open just to figure out where it's going. HTTP works the exact same way. The routing metadata in the headers must be quickly readable without actually opening the payload itself. It acts like a remote control for the entire interaction.
Okay, part 3, methods and intent, actions and idempotency.
Now think of this breakdown as a cheat sheet for our network intentions. We've got our standard methods: get to fetch data, post to create, put to completely replace a resource, patch to selectively append or update, and delete to, remove. But the absolutely crucial distinction here is idempotency. Idempotent methods like get, put, or delete are completely safe to repeat multiple times. You'll get the exact same outcome on the server. But non-idempotent methods like post, they will create a brand new resource every single time you hit send. So you definitely want to be careful there.
Part 4, navigating cores, the security boundaries.
So by default, browsers enforce a strict same origin policy to stop malicious sites from hijacking your data. But as we know, modern web apps constantly need to make cross-origin requests. So how does it actually work? Well, the browser acts as a security guard. If a request uses custom headers like an authorization token or sends a JSON body, the browser hits pause. It first sends an options request, which we call a pre-flight. It's basically asking the server, hey, do you support these methods from this specific domain? The server then responds with its allowed capabilities. And only if the server gives the green light does the browser send the actual real request.
Next up, part 5, status codes, decoding the response. The absolutely crucial point here is memorizing this basic numerical map. If you do,
You can instantly diagnose network traffic without ever needing to look at a response body. It is a universal language. The 100s are informational, 200s mean success, we love those, 300s are redirects, 400s indicate a client-side error, and 500s, that means there's a server-side error.
Because when things go wrong, knowing exactly who is at fault makes debugging so much more efficient. If you see a 400 bad request, a 401 unauthorized, or the infamous 404 not found, well, that's on you. The client messed up. You either formatted the data wrong, your token expired, or you asked for a resource that literally isn't there. But if you hit a 500 internal server error, the server dropped the ball. The client did everything perfectly right, but the backend unexpectedly crashed or just couldn't process it.
All right, final section, part 6, optimizing the flow, speed and efficiency.
One of the absolute most powerful optimizations is caching. It acts as a massive shortcut for the network. See, when a server sends a resource, it can include an E tag, which is essentially a unique hash representing that specific version of the data. On the very next request, the client sends that E tag right back. If the data hasn't changed on the backend, the server doesn't waste time resending the whole payload. No way! It simply responds with a 304 not modified status code, allowing the browser to instantly reuse the local data it already has sitting right there.
And this optimization ties perfectly into the massive performance gains of content negotiation and compression. Using accept headers, a client can tell a server it prefers formats like JSON and that it supports compression like gzip. Visually, the impact of this is just undeniable. An uncompressed JSON payload that weighs in at a massive 26 megabytes can drop to just 3.8 megabytes when the server applies gzip compression. I mean, that is an absolute game changer for reducing server bandwidth and drastically speeding up client download times.
Finally, we have to talk about handling massive file transfers without just timing out the connection. We actually tackle this differently depending on the direction of the flow. When we push massive files out to the server, we use a multi-part request. This separates pieces of binary data with specific text boundaries, so the server knows exactly where one chunk ends and another begins. Conversely, when we're pulling a huge continuous response in, the server uses a text event stream. By utilizing a keep-alive connection, the server sends the massive file back to the browser in sequential, manageable chunks until the whole shebang is completely transferred.
Which brings us to the end of our anatomical breakdown. Knowing the strict rules, the metadata wrapped in the headers, the specific methods of intent, and the security boundaries of this entire conversation, how are you going to structure your next backend request? By mastering these underlying principles, you can stop guessing and start building much faster, more secure, and highly resilient APIs. Thanks so much for joining me on this explainer, and I really hope this empowers your next coding project.